Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We are very pleased to have John Reppy here with us today. John is a very well-known computer scientist working in the area of programming languages for many years. He's best known for his work on concurrent ML, and he spent many years at Bell Labs, after which he moved to the University of Chicago, where he's currently a professor. And he's going to tell us about the Manticore Project today. Welcome, John.
Thank you. Okay, so thank you all for coming. And this talk is both going to be really a work in progress talk, because this is a project that's ongoing, and we've been at it for about 1.5 years now. And it's also going to be somewhat of a core dump about what we've been doing, and so hopefully it will have some coherency to it. But please feel free to ask questions as we go along, and I'll try to provide details where there's interest, and otherwise keep things at a somewhat abstract level. So first of all, just to give credit to my collaborators, this project is a collaboration with Matthew Flewitt, who's at Toyota Technology Institute in Chicago, which is sort of right across the midway from us. And we have a number of students who've working on it, and some other people who are sort of peripherally involved as well. So, like everyone else, we're motivated by this multi-core revolution, I guess people call it nowadays. That's coming along and going to hitting the software industry quite hard. And our take on this is really that, a lot of people who've been interested in parallelism over the years have really focused on scientific parallel computing. And scientific parallel computing is actually, relatively speaking, an easy problem. Not to say that it hasn't involved lots of research over the years, but you're typically dealing with a particular algorithm. Very often these algorithms have very nice regular structure, so there's a lot of opportunity to take advantage of that. And you also have lots and lots of money, so you can put a lot of programmer time into making your programs run fast. And people have built these big computers, and they solve particular problems. And it's I think on the whole it's actually been a fairly successful enterprise. For multi-core, this is not. I don't think this actually helps us very much, because the applications that people run on their laptops are not big scientific applications, but rather things like computer games and multimedia stuff and whatnot. And these kinds of applications are not going to get faster unless they're written in parallel, in some way that is parallelizable, either in an explicitly parallel language or in using a parallelizing compiler. And so our motivation really is trying to come up with programming language mechanisms that will make it easier to write what you might call parallel systems programs. Okay, so programs that don't fall into the sort of traditional scientific domain, but rather are more like what you would typically run on a commodity computer. And one of the things that we sort of started off with as an assumption is that this commodity parallel hardware actually supports parallelism at a lot of different levels. You've got SIMD instructions, you've got simultaneous multi-threading, you've got multiple cores, you may have multiple processors and desktop systems as well. And also you may have heterogeneous processors, things like the cell processor. And so there's parallelism at a lot of different levels of granularity. Likewise, we believe that the applications that we're interested in will have parallelism at a lot of different granularity. That you'll have things like, just to, take something like a computer game, flight simulator, something like that. You may have you'll obviously have all the kind of graphics parallelism that you may be able to run on your GPU or on your using SIMD instructions. You're going to have things like physics simulation, which could take advantage of SIMD. You may be running multiple AI threads. You may be running running threads that are preloading geometry, doing level of detail simplifications, all these kinds of things. And it's not a regular structure. It's a very heterogeneous structure. So our approach to this is really, I mean, we were calling this heterogeneous parallelism, and what we're trying to really do is sort of provide a language design that kind of spans a lot of different levels of granularity, but in a way that's comprehensible. And one way to look at it is if you sort of think of languages as ranging from explicitly threaded to implicitly parallel, and somewhere in the middle are these sort of implicitly threaded languages. And what we mean by that is languages that have some sort of annotations on your program that say, okay, here's a good place to be parallel, but those annotations don't map into explicit threads. They map into a hint to the runtime system and the compiler that, hey, here's a good place to maybe to run things in parallel. And so what Manticore attempts to do is sort of span this range from languages like CML, Erlang, Java, I guess C# that have explicit notions of threads, and languages like Nestle and Nepal and and library sort of tools like OpenMP that have more implicit notions of threading and provide that sort of gamut. Now, one of the advantages, the advantage of being over here is that you're essentially writing sequential code with funny syntax, but it's much easier to understand what's going on. On the other hand, the advantage of being over here is that you really have concurrency, you have support for non-determinism, and that's important in systems applications. And so we really think that you need to have both of those to be effective in this space. So our project, as I mentioned, we've been working on this for about a year and a half. And there's sort of three aspects that I'll talk about in this talk. And it sort of represents maybe, you could say, the first phase of the project, because I think there's some other things we'll be working on in the future. But first, we've been thinking about language design to support this kind of heterogeneous parallel space. Second, we've been thinking about what you have to do with the runtime system to be able to support this kind of parallel programming, because if you're doing, say, explicit threading, you may be using, say, round-robin scheduling or some kind of load balancing, work stealing type scheduling techniques. But if you're doing implicit fine-grained parallelism, you're going to need different scheduling policies. And how do you fit these all together? And then we're also, of course, interested in actually making all of this work, and so we've been working on the compiler and runtime system and whatnot. So what I'd like to do is start off talking about the design, and then we'll talk a bit about schedulers and move on to the implementation. So one of the things we did not want to do is redesign general purpose programming languages. We really wanted to focus on the issues related to parallelism and concurrency, and so we took an off-the-shelf functional language, in this case standard ML, but this choice was mostly because we are comfortable with standard ML. Could just as easily have been some other language, and we stripped out all of the things that make parallelism hard, i.e. side effects, although we left exceptions in, and this introduces some interesting implementation challenges, and I can talk to you about that offline. I won't dive into them in the talk, but we sort of believe that exceptions are pretty crucial if you want to write real world applications, and so not having some kind of exception mechanism seemed to be too big of a sacrifice. But we got rid of mutable storage and things like I/O and whatnot. And of course, we we bring those back elsewhere, or at least we bring back I/O elsewhere. On top of the sequential core, we add implicit threading constructs, and these are largely deterministic. There's one exception to that. And so they have a sequential semantics. And then lastly, we have, on top of that, we have explicitly threaded parallel programming constructs, which are essentially, which is where you get back things like I/O and whatnot. So the implicitly threaded stuff is probably the most interesting. And what we wanted to do was provide a sort of a collection of different mechanisms. Some of these are have been around for quite a while, and some of them are fairly obvious. Some of them are maybe a little bit different. First of all, we have nested data parallelism in the form of parallel arrays. So this really goes back to Guy Blaylock's work on Nestle and parallelization Lisp, and more recently the work on Nepal and data parallel Haskell by Manuel Chakravarty. We have parallel tuples, which give you a basic kind of fork join type of parallelism. We have parallel bindings, which are a little bit like futures in a way, and they give you a essentially sort of more of a data flow kind of parallel programming model. And lastly, we have, and this is the place where non-determinism comes in, we have parallel choice, which is to support speculative parallelism. Yes?
So you said you wrote arrays, and now you have parallel arrays.
Yeah, I could call them vectors. I mean, they're immutable. The terminology in the literature is always called these arrays, even though they're not arrays in the sense of being mutable. So what do they look like? Well, the most important mechanism is this comprehension syntax, which essentially is a way to construct a parallel array, presumably in parallel. So you have some expression that you're evaluating for every element of the array, and you have some source of data values. So this is kind of like a for loop, parallel for loop, if you will, that builds a resulting array. And the key point about this is that you're allowed, this expression here is also allowed to be an array expression. And the arrays don't have to be rectangular. They can be irregular. And this is what Blaylock really exploited, to be able to code up lots of irregular parallel programming examples, things, sparse matrix multiplication, various kinds of computational geometry things, etc. And a lot of what he really exploited was this ability to use this irregular array data structure as a way to encode various kinds of other data structures, such as graphs and whatnot. And so the key here is that you have some xs or ys, which is an array, and for every element in these arrays, you're going to add those two together, and you'll get a new array that's the sum. And this is a zip semantics, not Cartesian product semantics. In data parallel Haskell, they actually they would take every pair, combination from xs and ys, and then but we use the Nestle approach, which is zip semantics.
Zip semantics means the first one with the first one, second
one. Right. Yeah. So it's a pointwise.
What if you run out of?
Oh, then you just truncate. So if the lists are if the arrays are uneven in size, then you end up with a result that's equal to the shorter size. And in the Cartesian product version, you end up with the if you have n and m, you n times n m results.
I also didn't understand what you meant by irregular arrays. Why are they irregular?
Oh, because they don't have to be rectangular. In other words, if you have an array of arrays, you could have, the first one could have, one element, the second one could have 100 elements, the third one could have one element, things like that.
I see.
Right, so it's, so for example, if you want to do a sparse matrix, you can do each row for the row in the matrix, and each row then consists of index value pairs. And then you can, and you can write, the sparse matrix times dense vector product is a really neat little one-liner. Yes?
Can you only iterate over arrays in this form, or are there other sort of collection-like things?
At this point, we can only iterate over arrays, although it would be very natural to try to generalize that to other kind of iterative structures. And one of the things that we sort of have been debating in terms of design is whether parallel arrays should be a different type than, say, vectors. Because on one hand, in terms of implementation, you may actually want to use a different representation. For example, Blaylock and the data parallel Haskell people use a flattening transformation, which is they take this irregular structure and they flatten it out into a single flat array with a second array that tells you where the breaks are. And the reason for doing that is if you're running on vector hardware, it allows you to just then chop it up into pieces. And the Nestle work and the Nepal work were really targeted at things like craze. So machines where the performance you got was going to be out of using the vector hardware. It's a very nice the flattening transformation is actually very nice because it also deals with things like the array of structs, destructive arrays transform automatically. So it if you want to go down that road with a completely flat representation that's very easy to divide up into parallel chunks of work, it's a very effective technique. We're not convinced that we necessarily want to go down that road, so this is something we're on the other hand, you get this non-orthogonality in the design because now you have say lists or vectors or something like that, which to all intents and purposes look like parallel arrays, except they're a different type. So just to give you a slightly more complicated example, this is the Mandelbrot set computation. And so this is, in this case, of course, you're doing nesting, but the result is going to be a rectangular product. And there's probably a missing type. Well, this should be a J, and there's missing type coercion there. So it's a small bug in the slides. But anyway, we actually have this. We can run it, and that's, in fact, that image, although it's a little dark on the screen, was produced by running this in Manticore. So it's a, it's proof of concept of nothing else. So parallel tuples. So the idea here, tuples are a natural way, of course, to, for example, to form arguments to operators as well as to group together a set of computations. So it's very natural to think, well, why not just compute the elements of the tuple in parallel? And so what we've done is we've just added these little bars there on the construct, and the idea basically is it gives you a kind of a fork join. So if this is a classic dumb example, but if you imagine a binary tree of integers at the leaves, and you want to compute the sum of all of them, at each level of the tree you can compute the sum of the two subtrees in parallel, and so essentially at each level you're going to do a fork and fork off two computations, although of course one of them can just be the same thread that was calling the function, and you'll do the subcomputations and then you bring them all back together. And of course if you actually run the parallel program on real examples, the parallelism overhead completely dominates, and it's much slower than sequential until you get to very big examples. But the idea here then is that at each level of recursion we split into two things, again split into two things, and then come back, and then come back. And so that's a fairly straightforward idea. Parallel bindings. So a lot of what we've done is gone through the sort of existing sequential mechanisms and tried to find places where it would be natural to have a parallel version of the construct. And so this is now an example over the same kind of binary tree, but where what we're going to do is we're going to compute the product of all the leaves. And if we at some point in the computation we hit 0, then we know the result is 0. That feature will be important in a moment. But the basic idea here is that this variable b is going to be bound to, if you will, a future that's computing that the recursive call on T2, and then when we reference b down here, we're actually going to, at that point, we'll have to wait to see whether b has completed computing. So we're going to get parallelism by essentially using a kind of future-like mechanism to do this. But the other point is that if we end up in this branch because A turned out to be 0, then in fact we don't need to compute B, and we can at that point cancel B. And one of the things is this stuff work. A lot of these things work because of the fact that we're working in a space without side effects, and so a lot of the correctness issues that we would have to deal with, or program analysis issues that we might have to deal with if we had side effects around, we can fortunately avoid. Of course, exceptions are the one. Oh, yes. Oh.
So there seems to be some asymmetry in this list.
Yes, there is asymmetry. And in fact, in this particular case, it's essentially, I mean, we actually now have an answer to that asymmetry, which I don't have a slide for, but I could sort of wave my hands about or scrawl on the board. But I'll get to that in a moment. So again, here, for example, if the leftmost leaf happened to be 0, then in the parallel computation we can cancel these guys, I guess. And so the computation would be something along these lines. These dashed blue lines represent the futures, and these red lines represent the red arrows represent the sort of cancellation messages. And I should mention, by the way, a lot of this design is very speculative. You know, we can look at the sequential design. We can sort of see natural places to introduce parallelism. Of course, there's a lot of ideas that people have suggested over the years about different structures for parallel computation. And a lot of what we've been doing in the past year has been building up the implementation infrastructure so that we can actually start to get an idea whether this stuff is useful or not. And so, I want to should take it all with a grain of salt, since we, yes.
Did you consider in your design trying to communicate to the underlying schedulers which computations were speculative and how much, and when they became non-speculative, so you could sort of bias the effort that was put into possibly useless work?
So the short answer is I guess I have two answers to that. So that's a problem that we're very interested in. Our preference to approaching that problem is actually to try to develop techniques that don't require user intervention. I mean, one of the things we're trying to do is sort of trying to keep the programming model as clean as possible. And when you start adding these kinds of user information about how the user thinks the program executions can behave, or I mean, location information is another example when you start to get into non-uniform memory architectures. It adds a lot of complication, and it may be necessary complication, but we're hoping that it's not. And so what we're more interested in is trying to use a combination of static techniques, static analysis techniques, to try to figure out places where it might be useful to instrument the code. For example, if you know the sizes of trees, you can make better decisions about scheduling. I mean, one of the key points of an example like this is that you really, when you get to a tree smaller than some size, you really want to run sequential code. You don't want to run parallel code. And if you have instrumented your data representation so you know the sizes of the trees, then in fact you can make that runtime check. And so one of the things that we would like to be able to do is sort of automatically transform the data representations to include instrumentation where it's profitable. Use that. And I mean, another obvious possibility, of course, is using profile-based feedback to running programs on training data and trying to use that as a guide to figuring out things. But these are all, I mean, in some sense, that's stuff that we're all very interested in, but we haven't really gotten to a point where we could attack those problems effectively. We need to have an implementation and an example programs and whatnot to be able to really to evaluate those kinds of questions. So I think we're at a point where maybe this summer we'll start to tackle some of those questions. So parallel choice is the one is in fact the place where we can start to deal with this asymmetry. And this represents our sort of first design of parallel choice, and we actually have a newer, more general operator which I could sketch on the board, because it's, I mean, even as of Monday we were still playing with the design space, so it's still very somewhat up in the air. But the basic idea here is that you evaluate two expressions in parallel, and you're free to the implementation is free to return either value. And the order, I mean, one assumes that it will return the first value it gets. Now this is very limited in its expressiveness, because it really doesn't let you look at these values when making the decision about what you want. So an obvious extension, an obvious example of something you might want to do would be, say, a short-circuited Boolean operator, right? Where if you have and you get back a false, you can say, I know the answer is going to be false. Or if you have or and you get back a true, you can say, I know the answer is going to be true. But otherwise, you wait for the other answer. And so we've actually come up with essentially a generalization of the case construct in ML that we call p-case. So if you take and this is actually a little bit reminiscent of the join calculus, if you're familiar with that. The basic idea is you're going to have some expressions that you're going to want to run in parallel, and then you're going to have some patterns that you're going to want to evaluate those against. And you're allowed to put underscores here. An underscore has a somewhat different meaning than it does traditionally in pattern matching, because it's not any value. It means also no value yet. And so it will match the fact that we don't have a value yet. And you can then start to, if you want to do this parallel and example, you could do, if you get false, then you false, and likewise for true, likewise for the other side. And otherwise, if you get, so that in this case, you evaluate these guys, and if you get back a value here, a false, you can short circuit. If you get back a false here, you can short circuit. Otherwise, you have to wait for both values. So this is very much like join patterns.
So that lets you observe side effects and steps outside of the pure functional realm, right?
Oh yeah, this is non-deterministic, right? So I won't describe as side effects.
You're getting to see that he got done, which means he can signal you.
Well, but he doesn't exist in subsets. I mean, there's no language level notion of a thread that you can observe here. It's an underlying. For example, a valid implementation of this would be evaluate E1, then evaluate E2, or evaluate E2, then evaluate E1. Another implementation might be, an interleaved implementation where we compute a little bit of E1, then compute a little bit of E2, etc. I mean, there are lots of different possible implementations. All you can see is that when you see this, all you know is that this value is done, and it turns out to be false. This value may or may not be available. You don't know.
So it's not that It's not that underbar matches not done yet. It's that
it matches anything, including not done yet. Right. Yeah. So it's okay. Now there's some interesting issues and something. I mean, there are a couple of weaknesses of this mechanism. Still, one is that these things are not first class. So you can't write, for example, a function that implements this pattern, because functions are strict in their arguments, and you would evaluate the expressions before you call the function. You wouldn't get, so we're starting to think that we may in fact need to actually introduce futures or something like futures concretely as a type. The other issue that we've been dealing with is the question of what if these things raise exceptions, and should we be able to deal with exceptions in this? And we have a sort of tentative design that does that. And one of the reasons why you want to be able to deal with exceptions is it lets you then essentially implement a kind of abort mechanism for speculative parallelism, where you can, by raising an exception and by having the appropriate patterns in your recursive splits, you can cause branches of the computation to be short-circuited or eliminated explicitly in the so that's something we're playing around with, but it's all very still very rough. Okay, and lastly, I just want to say something very quickly about explicit threading. So the coarse grain parallelism and explicit concurrency is based on concurrent ML, which has been around for a long time. And the key point is we have explicit thread creation. So these threads, the language you can really talk about in the language, they really exist. We have message passing, and more importantly, we also have the CML-style event combinators for building synchronization abstractions. And as far as the design goes here, we're still pretty much doing straight CML, so there's nothing really new there.
Just a general question. I mean, what would be lost if we gave up this part? I mean, and the reason I ask that is that correctness could be a real issue, right? Because the interaction of explicit threading with, all the implicit mechanisms.
Well, so if you put aside p-case and choice for a moment, the rest of the implicit threading constructs have a sequential semantics. In other words, there's a program transformation you can define to translate it into just straight sequential standard ML, and that will give you and the implementation needs to respect that semantics. To deal with the choice, you need to throw in McCarthy's AMB operator to make that work. I believe systems programming has to involve concurrency. I mean, fundamentally, I think it's very hard to say write an interactive application if you don't have concurrency. You effectively end up writing. I mean, in the old bad old days, I mean, when I did concurrent ML, the standard practice for writing interactive applications was purely sequential and involved, these horrible event loops and the inverted control flow and all this other awful stuff. And I think we finally have gotten away from that. I think people largely now recognize that, in fact, interactive applications are inherently concurrent applications. And I think you could say the same thing for networked applications. And also, I think that when you start to talk about when you start to talk about really heterogeneous parallel computations, you can sort of force them into this implicit threading model. And I mean, I think if you just look at the work that Guy Blaylock has done, it's very impressive how much you can force into that model. But it starts to get very artificial, because you're essentially you're taking computations over completely unrelated computations, and you're sort of saying, oh, these are going to be in a parallel tuple, or these are going to be in a parallel inside a parallel array, or something like that. And it really that may be a sufficient way to get the parallel to code up a lot of the parallelism, but it becomes a lot of what it becomes is how do I take my notion I need these 5 different threads doing 5 different things and turn it into something I can express in this much more restricted language. So I actually think that explicit concurrency is really crucial. The thing that we're exploring that and talking among ourselves a lot about is the sort of relationship between these different mechanisms, and that this stuff here really sort of sits somewhere in the middle, because it has non-determinism, but it doesn't have an explicit notion of threads. And we've talked about ideas of something sort of analogous to call CC that would be give you a way of reifying the actual thread that you're running with, and that's an interesting idea. I don't know what it means though.
instead of this explicit construct, you reuse something like monadic concepts or called CC kind of stuff.
Yeah, no, I'm, in some sense, this stuff's been around for a long time, and it's been used by a lot of people, and I mean, it's also been used in a lot of different languages as well. And I think it's reasonably solid. I mean, obviously I have a biased opinion here, but I built some big applications with it. I know commercial applications have been built with it. I know that people have thought it was neat enough to put into their language implementation. So it's got a certain amount of use over a fairly wide community, and we know what the limitations of the mechanism are. But on the whole, I think it's been pretty good. And so it's an easy thing to do in terms of the design space, because we don't have to. We do have to think about how to implement it in the parallel implementation, but we don't have to think a lot about the language design questions. And so we in some sense, we sort of said, let's take this. I also should say that I think Erlang, right, so Erlang really is just a first order functional language that has message passing, right? And essentially anything you can do in Erlang, you can certainly do in concurrent ML. What we're adding here that Erlang doesn't have is this implicit threading constructs. And the key point here is these threads may actually involve multiple parallel fiber. So we actually use, to keep the naming straight, we call them fibers. So they can involve multiple implicit threads inside, and so that we actually have this sort of like two-level design.
Okay. I have a question.
Oh, yeah. Sorry.
Previous slide.
There.
How do you use semantics to a program which has the spawn?
Well, I have a I mean, there actually been several published semantics, and you can actually go all the way back to a paper by Robin Milner and a few other people in Popple in '91, I think it was. They gave a kind of labeled transition system semantics using, or it was sort of a combination of a natural semantics and labeled transition system. I have a semantics that's sort of like a chemical abstract machine style approach of a soup of processes. And I had a version in my dissertation and another version in a book that I wrote about concurrent ML. But there have been a couple of other people but they've all been basically operational models.
I just wanted to get an idea of roughly what's going on. Is it that all these channels, they're like global variables, and then there is a control program counter associated with each thread gets spawned, and there's an interleaving semantics that in each step one thread gets to go, and then
that is a valid semantics. Yes, I mean so the only way the threads interact is when two threads are communicating over the same channel. And so there's a global in my semantics. There's a global set of channel names, which are different than the channels in the in the program, obviously, because you have lexical scoping and other techniques that you can hide information inside in the program. But underneath the hood, there's this global set of names, and if if thread 1 is sending a message on this channel and thread 2 is receiving a message on the channel, then you can.
Now a follow-up question. In a language without any side effects, to give semantics to it, you don't really need the notion of a state. It's basically this kind of an input-output thing. You don't need the notion of a state transition. In a purely functional language without side effect, as soon as you add spawn, you start to having to deal with state, right?
Yes, right.
In the semantics even.
Yeah, no, I mean, it's well known that you can implement state using threads.
I see.
I mean, you can, I did in my dissertation. I gave it a code, and you actually also implement the fixed point combinator too. So you can, which is really just the observation Matthias Blyson made that if you have ref, you can implement fixed point. But so you could actually start off with a very weak functional language without recursion, without explicit state. You could add these primitives, and then you get mutability and you get fixed point operator. So yes, it adds a lot. I mean, I mean, from a formal semantics point of view, throwing this in certainly makes a big difference. From a sort of practical language point of view, it's what we deal with on a daily basis. So, okay, is that right? Okay? So that's the sort of quick tour of the language design, and I wanted to now talk a little bit about scheduling. So one of the problems that we sort of faced early on was this question of, if we're going to have these explicit threads, and just for sake of argument, let's assume they use round robin scheduling, and then we're also going to have these kind of parallel constructs where we're maybe a given language level thread or explicit thread is going to create a large number of fibers that then will need to be scheduled, maybe a gang scheduler, maybe lazy task creation or some other scheme. You have to, how do these schedulers interact? And we've basically come up with an architecture for that, and I think we've satisfied ourselves that the architecture at least is very expressive, and we're sort of in the process of trying to understand whether it's efficient, and I have some data toward that point at the end of the talk. So we have three notions of process abstraction in our system. We have fibers, which I mentioned before, which are just essentially they're just continuations. And they really are the sort of, it's just a piece of control flow, right, and environment. Then we have these threads, which correspond to the explicit things, the things created by spawn. And essentially what they are is a fiber plus some sort of ID. In fact, what it really is it's a fiber plus thread local storage, and in that thread local storage you could store an ID and you could store other stuff. And I should mention, thread local storage here is an internal implementation feature. It's not a surface language feature. And then we have this notion of virtual processors, which essentially are our abstraction of the computational resources. And in our implementation, these are just P threads. Yes?
What do you mean by nested schedule?
I will see in a moment. So the key point about nested scheduling is that if you have, so you do something like, spawn, some stuff, and down here you go, f of x, x in x's, right? So this, right there, that computation could end up, needing 8 threads to make use of an 8-processor machine, and it's going to have to be that scheduler for these 8 threads. In substance, is nested inside this thread.
But is the idea that I might want different types of schedulers for different types of parallelism?
Yes. Oh. Okay. And one of the things we've been doing is exploring a number of these things. But it's also the case that we have this fixed set of resources, and we're sharing these resources among language level threads as well as independent parallel computations. Oh, yes.
Instructs to convert a thread into a fiber and back for some OSs.
You mean in the source language? No. The fibers are completely. The fibers essentially are in the compiler / runtime system. The fibers are the representation of something that can be run on a processor, and but they're not. They don't have a visible manifestation in the language. Yes.
Fairness model at the thread level that is implemented in scheduler design?
In CML there is, and I actually put quite a bit of time into thinking of ways, sort of efficient ways to implement both event fairness and process fairness in CML. In our current implementation, we don't actually have that support yet. And what I did in terms of the semantics and fairness was essentially, the semantics allows you to have, defines, for a given program, defines typically an infinite set of possible executions. And you can, since fairness is really only a property over infinite executions, you could filter out those executions which aren't fair, and essentially, as a side condition, say, okay, an implementation should only allow executions that correspond to fair executions. How you actually end up implementing that, of course, is quite tricky. And what we basically did in the CML implementation is used essentially kept track of how often communication primitives were involved in a possible communication but didn't actually get picked, and used that as a way to sort of increase their priority, so that eventually they would get picked, because they would over time the priority would evolve to be a very large number. But anyway, but in our current implementation of Manticore, we do not have we haven't dealt with fairness, and that's something we'll have to do. Okay, so our scheduling model is based on a notion of schedule actions, and this is an idea that Olin Shivers had proposed as a way of bringing sort of machine level events like machine level exceptions and interrupts, I guess is the right, into a programming language model. And so we have, fibers again are just, a suspended fiber is just a continuation of no arguments. And a scheduler action is really just a continuation that takes a signal. And we actually have one other kind of signal, but for purposes of this discussion, there are two types of signals that are interesting. Stop basically means that the computation that's running is done. So that's how you sort of would do thread exit. And preempt is that the runtime system has decided that that processor should do a context switch and run some other computation. And so the basic idea is that we sorry, I need to give a little bit more detail. So the basic idea is that we have these vprocs. Each vproc has a local queue of threads. It has a mask bit which allows you to locally mask preemption. It has a currently running fiber, and it has a stack of actions. And it's by using a stack of actions that we actually support nesting of schedulers. And we have 3 operations that work on these vprocs. So the first operation, which is run, which is essentially, you have some computation, some fiber, and you want to run it on the vproc. What you do is you provide one of these actions or scheduler actions, and you provide the fiber, and you start running. And so it's just going to push the action onto the stack and start running the fiber. We have preemption, which is something delivered by the runtime system. And what it does is it captures the current state of the computation as a fiber and wraps it up in one of those signal preempt signals and passes it to the topmost scheduler action. So in this sort of simple preemptive scheduling situation, when you start running the thread, you push on your preemption handler. When the preempt signal comes along, it gets popped off and deals with the signal. And then the other mechanism we have is forward, which allows the current, which is typically used by scheduler actions themselves to push signals up the stack. But it can also be used to implement thread exit, because if a thread calls forward on stop, then that effectively passes the stop signal to its own scheduler action. So let me give you a graphical description of these, because it may be a little bit easier to follow. So run, again, if we're doing run with some action, and F is our fiber, what will happen is the action gets pushed onto the stack, and we start running here by transfer control to the continuation that represents that fiber. And the other thing to notice here is that that run is always done from a preemption masked state to one where preemption is now enabled. If you don't do that, you get nasty race conditions. And preemptive essentially goes the other way, takes captures the current execution as a fiber F, takes the current action, masks signals, and takes this action and passes in preempt, and F here is the suspended state. So this action here, for example, was implementing round robin scheduling, could just put F into this queue, get something else off of that queue, and call run on it. And that would be how you do just a simple round robin scheduler. And then lastly, the forward operation can be used in either a masked or unmasked state, but it always leaves you in a masked state. And it just takes the signal and passes it up to the next action. So it's a very simple mechanism. I mean, there's not a lot to it, which of course makes it easy to implement correctly, which is nice. One of the points about it is that the schedulers are actually distributed, in some sense, distributed programs. They're distributed across all of the vprocs that are in the system. And so writing the schedulers can be a bit of a challenge because they have to coordinate across these multiple vprocs. And one of the things that we use the thread local storage for is essentially providing the data access to the data structures that might have, for example, if you're doing some sort of work stealing or other kind of mechanism, the hooks into those data structures are provided by the scheduler, not by the core runtime system, and access to them is gotten through the thread local storage. So at any given time, so here we have 3 language level threads. The first one is just has a single fiber. The second one has 3 fibers, and the third one has 2 fibers. And at this point in time, the blue one here is running on the first and last processor, but here it's queued up, and the green thread is running. And over here, in this machine, the purple thread is running. And here, the purple thread is queued up. And so at any given point in time, you're not necessarily going to have your computation running on all the resources, but the schedulers effectively are providing the kind of process abstraction or processor abstraction or multiplexing of the processors. Yes?
How do the fibers get created in the threads?
Well, they get created by essentially they're continuation. The fibers are just continuations, so you create continuations. Give me a
situation where 2 continuations would
well, so you do this. So if you have a spawn, and then inside the thread that you're spawning, you do a parallel array. Right. So that's the in some sense this is where the 2-level design comes from. Now, one of the things I should say about the implementation, let's just make sure I'm not getting ahead of myself. I'll get to that moment. Okay. So anyway, so that's let me say, so this is our scheduling infrastructure, and a lot of the schedulers essentially are small programs written in a kind of unsafe version of ML that then get run through our compiler. But we've explored a lot of different scheduling policies using this design. We've got, basically one of my students who's worked this is Mike Rainey has sort of been going through the literature, the parallelism literature, and looking at various things that people have proposed over the years for ways of managing parallel computations. And so he has, he's looked at lazy task creation, he's looked at some of the stuff that Silk people have done, including lazy task creation, some of the thread stealing, he's looked at gang scheduling, at engines and nested engines from the scheme community, and various, and some of the, I think he's actually even looked at, may have looked at some of the real-time scheduling disciplines. And largely what he's looked at these from the point of view of is this framework sort of expressive enough to handle these things. One of the things that we're now starting to do is actually try to do some empirical evaluations of these different schedulers and understand where the overheads are and ways to make the implementation faster. And but we haven't actually sort of committed to particular scheduling policies yet. Yes.
So one thing that's not clear to me is how a fiber ends up in a particular vproc queue, and you said they move by stealing. So is that the only way? Is that you just end up wherever you?
All right. So there's something which I haven't mentioned here, which is there's a provisioning mechanism. So when you are going to start a data parallel computation like this, the provisioning mechanism is actually provided by the runtime system, and essentially it's a sort of way to say, I would like a certain number of processors, and the runtime system sort of says, here you can have this number of processors, which may be fewer than you request. And that's, of course, there's a whole piece of work that we have to do about thinking about load balancing issues and provisioning. Right now, the provisioning system basically always satisfies, always gives you what you ask for. And that's probably not the right thing to do forever. But that gives you a handle on the vprocs. There's a mechanism whereby you can put a fiber onto a remote vprocs queue. It's actually not done through, there's a sort of secondary, what we call a kind of a landing pad, which is actually where you put stuff. And part of that is just we're trying to keep the fast path synchronization overhead down and have these things which require synchronization between multiple processors to use other paths. Yes?
So when a thread is created, does it come with kind of a default fiber in it, or is
yeah,
there
so this guy is a thread that's just running by itself, and its fiber essentially is its state, if you will. If you have a thread control block or some notion like that, that's what a continuation is, and so at any given time, a thread always has its fiber, and then it might, if it's doing parallel computation, implicitly threaded parallel computations, it may have more than one fiber. So.
But there's this always semantics that the fiber is essentially, it's a non-preemptive unit of scheduling. You cannot preempt a fiber. It has to preempt itself.
So actually, in some sense, semantically, as far as the fibers are concerned, they don't see preemption. The scheduler actions see preemption, and you can implement a scheduler that effectively completely hides preemption from a fiber.
Yeah, but in the language, if you look at your primitives, you can actually preempt a fiber, right?
Well, if you're running a sequential program on your machine, and the operating system preempts you, you don't know that. It's not visible to you, right? It happens, and then you resume. And we can do exactly the same thing as far as a fiber goes. So if we need a way if we want to have create the illusion that a particular computation was never interrupted, we certainly can do that. And it's just exactly the same way. You capture the state and then you resume it later. But if you want to make it, if you want to make preemption visible, we can do that as well.
But that's not true, right? For example, I create a thread, then that creates a fiber, which is going to go try to send or receive something on a channel. It gets preempted just before that. And then some other thread gets scheduled, its fiber runs, and it changes the state of the channel. Now, when you resume the first thread, the global state is different. So preemption did cause a change in the behavior.
Okay, so I think that if you're using communication primitives, then you're in a regime where this whole idea of being isolated, of sort of pretending that you're really just a pure sequential computation doesn't make sense anymore. So I would agree with that. But and in fact, you don't even need preemption for that because you have multiple processors. So other processors could change the states of the channels as well. Okay, so let me, since I see I've now used up my hour, I should speed up. So compiler's very straightforward, series of IRs. The ones from the point of view of parallels and the ones that are interesting, we have a typed AST that we do transformations on, and we have a sort of Drek-style lambda calculus representation. One of the things that we've done is we actually go to an explicit CPS representation, and in fact we use heap allocated continuations like the standard Melbourne, New Jersey compiler does. This may not be the best choice from a sort of raw performance point of view, but it makes all of the concurrency and parallelism stuff a lot simpler, because continuations are just values. There are a whole bunch of nasty race conditions that come about when trying to deal with things like context switching and whatnot that just disappear because of the fact that you're not dealing with mutable, say, stack frames, or you're not trying to share stack frames between two different threads. So it in terms of sort of getting something up and running that works, it was a big win to go this route, and we may want to revisit it eventually for performance reasons. But yes.
So communication on channels, I'd be interested to know how it can be represented at the CPS level. I'm not aware of.
Okay, that's a whole other talk. So I'd be happy to talk to you about that, but maybe I could push that off.
Was there, just a brief question on that, was there any importing of ideas for PyCalculus for that particular layer of representation? I mean, PyCalculus has connections to the sort of surface language, not so much to the implementation. Okay. So in the AST level, we do. This is where we will. In fact, we haven't really implemented this yet, but this is where flattening that I talked about earlier would get done. What we do have implemented currently is introducing futures, and so these are futures that the implementation uses, not that are visible at the language level, but all of the implicitly threaded constructs are basically compiled into futures, including even the data parallel representations. And these are futures that support cancellation as well, and in some cases we can recognize that the futures have a kind of one-shot. They're a little bit like one-shot continuations that they only ever get touched once, and you can use slightly optimized protocols for those. And we also deal with pattern matching, that's sequential. Just to give you an example of how futures work, this is that tree multiplication example again, and now the p-val just really becomes future of the computation, and then down here in the then branch we would introduce a cancellation of that, and in the else branch we would introduce a touch. And so that just works. What does that do at the operational semantics when you put future tree multi T2?
Well, the way to think about it from the point of view of sequential semantics is that future is like delay, and touch is eval or force, and cancel is the no-op, the absorb, does nothing. We do a lot of standard optimizations at the lambda calculus level, although we need to do a lot more. Let's see David here, but we use David Tardidi's uncurring transformation, and one of the things that our compiler does is it uses these things we call high-level operators, which are essentially sort of, in some sense, they're kind of specially annotated functions that we can use. We could do rewriting to do domain-specific optimizations, because essentially you essentially do pattern match-based rewriting for that. And eventually these things get expanded, but they're actually defined outside of the compiler. So one of the things the compiler basically does is sort of sucks these things in. So all of the future operations and the scheduler, all the runtime system infrastructure, other than a very, basically other than the sort of very minimal stuff that's implemented in C, is implemented in terms of these high-level operators. And the compiler, so this both makes it very easy to try different schedulers, because we can easily just put in a different implementation, or in fact we can actually pick the scheduler as a command line option. But it also allows us to make visible to the compiler all of the stuff that's going on in terms of the runtime system and thread scheduling and things like that. And so eventually, once the compiler actually does aggressive optimization, we should get some benefit from that. So this is sort of I guess probably summarizes what I just said. And one way to think about these, and also I should mention things like spawn and the message passing operators and whatnot are implemented this way as well. One thing about, so even things like run and forward are done this way, we have the compiler basically knows about the data structure that represents the virtual processor and is able to, and so operations on that data structure just basically turn into loads and stores on that. And I mentioned the DSOs as well. This is, so we're into runtime. Okay, so this is fairly straightforward. vprocs are pthreads. Our garbage collector is one of the things we've done throughout the runtime system design is try to maximize separation between different processors, and so the garbage collector is designed to basically only involve synchronization between processors when you're doing a global collection of the global heap, and we use the Dolager-Leroy-Gontier collector to achieve that. And that's basically how we deal with the local heaps. Some pictures, I think. Yeah, so this is roughly what things look like. You have the vproc state, which actually turns out lives at the bottom of these heaps. Local heap data can point into the global heap, but global heap data can't point down. And so one of the big, if you have data structures that are shared among vprocs, those have to be pushed up into the global heap, and that's something that we're in the process of evaluating what the impact of that is. This is just the Appel collection, so I'll skip through that because that's old stuff. Global collections, we actually have a parallel collector for the global heap. It hasn't been heavily exercised, but it's basically designed to excuse me. It's basically designed to try to preserve locality between processes. So the data that a particular processor has created and pushed into the global heap and still has access to, we'll try to get that into the same subregions of the global heap if possible. And so the approach we take to that is essentially that each processor is responsible for chasing its own root set. And if one processor ends up with nothing to do, then we don't try to load balance. We don't try to have it steal work from the other guys. It just shuts down. It essentially stops and waits until everyone else is finished. So there's a great imbalance in the data structures. Like one processor has a huge data structure and all the other ones don't. Then you'll essentially reduce the sequential collection. But on the other hand, I think in practice these data structures will be spread out a bit more evenly, at least that we hope, and that we'll be able to keep essentially avoid things like cache pollution and other problems that could be an issue down the road. So we've been building implementation for about a year, a little bit more than a year, about 15 months, I guess. And our current language implementation is actually only core standard ML. We actually use the front end from a compiler course project as our initial front end, and then I had an undergraduate sort of beefed it up to support stuff that had been left out for the course. The compiler, though, basically produces running code for the x86 64. We have a runtime system, and actually this but not global GC is not true. The global GC does exist. I didn't update the slide. And it works on Linux and Mac OS X. We've got some of the BOM optimizations implemented. The CML stuff has also been implemented. Most of the implicitly threaded constructs are implemented. Some of the things like pcase are not done yet, but the p-val and the parallel arrays and the tuples are all implemented. And we've been doing as of a week or two ago, we started actually trying to benchmark things, try to understand our performance problems. And most of this work has been really focused on trying to test different schedulers and the efficiency of those schedulers. So this sort of doesn't really represent quite an end-to-end type test, but rather tests that have been biased toward well, let's try lazy task creation, or let's try gang scheduling. And our sort of preliminary results are, in fact, we can get good scaling if we use our own sequential implementation as a baseline, which of course is not really kosher, but if we do that, then things look really nice. But if we use a reasonably quality SML implementation, things don't look quite so good, and I'll show you. So this is our speed up curves using our own sequential performance and we're getting pretty close for a number of these standard parallel programs. We're getting pretty close to perfect speed up. Barnes-Hut I think, is not quite so good, and that has to do with the fact that there's a substantial chunk of non-parallel work in the particular version that we're using, which is the construction of the quad tree. And that looks nice, but to give you truth in advertising, this is the curve if you use standard ML New Jersey as the baseline, and we're taking about a factor of 2 performance hit in that case. Although for some reason Barnes-Hut does better, and we haven't actually figured out why that is. But the bottom line is that our sequential performance, is somewhere between a factor of 2 to a factor of 3 slower on these benchmarks than the standard ML of New Jersey performance. So we have a lot to do in terms of just basic sequential compiler stuff. And this is not rocket science. It's, we can go back and we can look at papers and theses that people have published over the last 10 years that say it's just pick out algorithms and hack them in, and that's what we're going to do. I mean, the main reason we haven't done that is that we didn't want to put implementing sequential compiler technology on our sort of critical path of trying to get the parallelism stuff working. And this image was actually generated by our ray tracer. So this ray tracer program is an id program that we translated into Manticore, and this center sphere, the material properties are really, I think, bogus, but the center sphere is actually transparent, so you can see things peeking through. But anyway, I guess I've already answered lots of questions, but I'd be happy to answer more if there are any, or if everyone's ready for lunch, that would be good too.
More questions? Other less time speakers?